So the wake-up tree for the MCS barrier is a binary wake-up tree. Once again, here there is a theoretical result that backs this particular choice, that the shortest critical path from the root to the last awakened child is shortest when you have a binary wake-up tree, and that's the reason that they've chosen to have this construction. Even though the arrival tree is a 4-ary tree, the construction for the wake-up tree is a binary tree. And let me explain the construction of this binary wake-up tree. Every processor is assigned a unique spot again. So P0 at the root, and P1, P2 over here, P3, P4, P5, P6, and P7. So that completes the 8 processes for this binary tree setup for wake-up. And the data structure that is used in the wake-up tree is as a child pointer data structure. And the child pointer data structure is essentially a way by which a parent can reach down to the children and indicate that that it is time to wake up. So that's the purpose of this child pointer data structure. And once again, as you can see, depending on the particular location in this wake-up tree, they may have children, they may not have children. So P0 has 2 children, P1 has 2 children, P3 and P4, P2 has 2 children, P5 and P6, P3 has 1 child, P7, and that is it, because we have 8 processors, and therefore these guys don't have any children, P4, P5, and P6. So in terms of wake-up, what is going to happen is that when everybody has arrived at the barrier, P0 is going to be noticing it through the arrival tree. And so now it says, oh, it's time now to wake up everybody. And the way it does that, it has a specific pointer to reach into P1 and signal to P1 that it's time to wake up. And similarly, it has a specific pointer in P2 to wake up. So a particular memory location, which is a pointer to a location that this guy is waiting on to wake up. So it's going to do that. And so what is going on is that, again, this is another important point, that in order to know that it is time to wake up, each one of these processes is spinning on a statically determined location. P2 is spinning on a particular location here, and P1 is spinning on a particular location here. And so when P0 signals P1, it is exactly sending a signal to P1, and it is not affecting any of the other processes. And similarly, when it signals P2, it signals exactly P2 using this pointer. And similar, once P1 and P2 are woken up, they can march down the tree and signal P3 and P4 and signal P5 and P6 by using the statically assigned spots that the children are spinning on to indicate that it is time to wake up. So the key point I want to stress again is the fact that in this construction of the tree, by design, we make sure that we know our position in the tree and we know exactly the memory location that we have to spin on in order to know that it is time to wake up. So these red arrows show the specific location that is associated with each one of these processes in the wake-up tree. So once the parents signal the children and they march down and signal all the other children, then at that point everybody is awake and the barrier has been reached. So the key takeaway points with the MCS tree barrier is that the wake-up tree is binary, the arrival tree is 4-ary, and there are static locations associated with each processor, both in the arrival tree that we saw earlier and in the wake-up tree. And through this specific statically assigned spot that each processor can spin on, we are making sure that the amount of contention on the network is limited. And also, by packing the variables into a single data structure, we can make sure that the contention for shared locations is minimized as much as possible.